Okay, so let's start this week's meeting. We have a newcomer this week, Nanali. Would you like to give a brief introduction of yourself?
Hello everyone, it's nice to meet you all. My name is Nia Lashkarashvili. I study at San Diego State University, Georgia, and my major is computer science. I'm really interested in learning deep learning, and as I know you're also very enthusiastic about it, so it's great to be part of your team.
Okay, thank you. So today we have three presenters, Robin, Jiayun, and Renbeck. So we can move on to our presentations. Robin, would you like to come first?
Yeah, sure. I will share my screen now.
Okay.
So can you see that?
Yeah.
Okay. Yes. This week I want to talk about the batch normalization, and batch normalization is a method that helps to speed neural network training. And the basic idea is that we shift and scale this input to every layers of our neural network. So if you see the below graph, it is a 3-layer neural network. And for the batch now, we will normalize every layers before we put this ZI to fit into our neurons. So in the third layer, we will have these ZIs coming from the previous layer, and we want to gather W3 and B3 so that we can optimize our models. And what we do is that we will first try to normalize this Z3, then and feed into the activation function. So we can see the implementation detail of this method. So given some intermediate values in neural network Z1 to Zn, we will first calculate its mean, the mu value, and calculate the deviation, the sigma square, and we will calculate each value z norm I, which is the origin value zi subtracted by the mean value and divided by the sigma square. And the epsilon here is the error term, so it doesn't really matter. But what we do here is that we shape our value to let it center at 0 and with standard deviation 1. But we don't want to have this strict normalization. Instead, we will train two hyperparameter gamma and beta so that we can center it at any position with any value of standard deviation. So in this node, we can see how we can fit our batch norm with our neural network. So in each layer, before we put our input zi to the activation function, we first normalize it by our batch norm. That is, we first calculate z tilde I here, and then we use our activation G to output the AI here. And recording each layer, we use the Zi equals to Wi AI minus 1 plus Bi. So Wi here is the weight and the Bi here is the offset. And this value is coming from the previous layer. So when we calculate z tilde I, we first normalize Zi by subtracting the mean. So the value Bi here has no influence on the result. Therefore, in each layers, we have 3 parameters, the Wi, gamma I, and beta I. And frequently, we'll combine this with our mini batch. That is, we train this parameter with respect to x1 to xn, where xi is the ith batch of the training data. So if we use gradient descent as our optimizer, the algorithm can be summarized as below. So for t equals to 1 to n mini batches, we first compute the forward propagation on xi. In each hidden layers, use batch norm to replace zi with our z tilde I. And then we use back propagation to compute dw, d gamma, and d beta, and we update the parameter just as how we do in our gradient distance. So you can also use like add an optimizer and combine it with batch norm. And here are some benefits of using batch norm. The main benefit is that it can help speed up learning. Since like we normalize the inputs to each layer, the changes in the previous layer won't have much influence on the next layer. And batch norm also have slight regularization effects, since we shift and scale our data only based on a single batch. We add some noise to each hidden layer's activation in a neural network. So however, the effect is very slight, so sometimes we want to use it together with other regularization methods like dropout. This graph might help to understand why batch norm can help to speed up chaining. So in our non-normalized feature, we have like the left figure, which has like a lot of oscillation. This is like similar what we talked about in our last meeting, but using the batch now, we will get like more like the figures on the right. We will like eliminate the internal covariance shifts so we can converge the algorithm faster. So yeah, this is all about the batch norm. Does anyone have any question about this part? So I guess it's all about this with my presentation. So yeah, thank you. I will stop sharing.
Okay, thanks Robin for your presentation of batch norm. So maybe then we can move up to Jiayun.
Okay. Right. I will share my screen right now.
Okay.
All right. So today I want to talk. Sorry about that. Today I want to talk a little bit about our convolution process. So when we're having a convolution layer, one thing that we need to do to like calculate this layer is like we can like if say that we have a like an image and then we can see the image as a matrix. So basically what we do here is that we are doing a matrix multiplication so that we will have a new output, and therefore we can develop on that to have a new layer, and then we can develop on that. So the cross correlation operation is just saying that we are having this kernel, and kernel is for this one for this for example in this picture we are having a 2x2 kernel, and then we are having a 3x3 input. So right now, for this square, we are just doing 0 times 0 plus 1 times 1 plus 3 times 2 plus 4 times 3, and then we get 19. And therefore, we have seen we see that a 3 times 3 input becomes a 2 times 2 output. Here is a generalization of how we will compute the output size. We can see it here that you just use your input size to subtract your kernel size plus 1 times your input width minus kernel width plus 1. That is pretty intuitive, and that's just like a background of why we are doing padding and stride, or why we're doing padding. So one motivation of padding is that we see that since kernels generally have width and height greater than 1, just as what we saw in the last example, we have a 2x2 kernel. Then after applying many successful convolutions, we tend to get output that the outputs are shrinking. So we have our output size is much smaller than our input size, and sometimes we want to keep the size of the output. So in order to do that, one thing we normally do is that you see here, we originally have a 3x3 input, and then we create a 5x5 matrix and fill the boundary with zeros. Therefore, we have a 5x5 input, and we do the kernel multiplication, and then we get a 4x4 output. So yeah, we had a 3x3 input, and we increase the size to 5x5, and then we get a 4x4 output. And then we are doing the same kernel matrix multiplications here. And the computation of the output size of the padding is this one. Oh, right. So yeah. So you're just adding the padding size. You're just adding the padding height, and you're just adding the padding width. Everything else is the same as the previous size. Okay, so right now, when we are saying padding and when we are talking about unit convolution process, we said that we are doing the matrix multiplication. We are doing the matrix multiplication for this one, and they're doing multiplication for this one and this one. It's like we are sliding the shaded area one by one, but actually sometimes we can do more about that. We can slide by 3, and we can slide differently for horizontally and vertically. Sorry about that. Right. So what do you mean by stride? So the stride is just, we refer to the number of rows and columns traversed per slide as the stride. So far we have used strides of 1, both for height and width. Sometimes we might want to use a larger stride. So the reason why we want to use a higher stride is that first of all, your output will be smaller, so you will be using less memory. Sorry about this. And then we can. Yeah, so our processing of output will be easier. This is like these tiers about memory and processing. And another thing is that we can make our model more easier so that we can prevent overfitting. So basically, that like these are the advantages of why a higher stride, and why why we want to do that. So in this example, we can see that. This is a two-dimensional cross correlation operation with a stride of 3 vertically. So we're vertically and 2 horizontally. So you can see this move to this one is 2, and this move to here is 3. So that we are just doing, and by doing this, we will have a smaller output. And if you sometimes you feel like the output is smaller, then you can also always do the padding. But just like I said, sometimes because that you want to prevent overfitting, so that's the reason of why maybe you want to change your stride. So right, so the size of the output after which we have our stride height and stride width into account is like this. So yeah, so basically that's it. Yeah. Yeah.
Do anyone has any questions or comments? Yeah. Actually, I have one comment is that I remember that there's some types of paddings like same padding and valid padding. So maybe later we can add these informations.
Okay.
Yeah. Okay. So if there's no more questions, then Thanks, Jiayun, for giving us the presentation about padding and stride. So next will be Rainback. Rainback.
Hello, can you see my screen? And can you hear me? Can you hear me? Hello?
Yeah, we can see your
Can you
screen.
see my screen? Okay. So, and also, before I start, can I ask, is there any like length requirement for the presentation? Like in terms of time or anything like that? Like for future presentation or anything? Like how long I can say, like what the time limits for the
Um, oh, you have a lot of stuff, right?
Yeah, just you wanted to ask, yeah. If, like how long would should be the presentation be? There's
Actually,
maybe
there's
not even
no,
today, but like in future.
yeah,
No?
there's no
Or
limitation, and yeah, we haven't set how long the presentation should be. So you can share anything if you would like to. Yeah.
okay. So yeah, I also wanted to talk about the like evolution of neural networks and build more on that. So far, so yeah, when we were previously we were just discussing the pros and cons of CNN architecture. I went into very interesting, let me say, a very interesting chapter for convolutional neural networks. And no, wait, it's not this. Wait, this one. So there's a deep learning book by Goodfellow Bingo and Corville. So this is very interesting chapter on motivations of CNN architecture. It like builds on like explains more in depth the pluses of convolutional networks. And first is sparse interactions. So to explain more, to explain more. So before in let's say in multi-layer perceptron, we used the neuromagic multiplication for the propagation, and each element in output was dependent on each element in the input. So everything was connected like over here. So yeah, now imagine like let's say for image detection or anything like that, we have for example 500 by 500 pixels image, and including like image channels, which is 3, we have input of 750,000 dimensions. That's a lot, like just for the input. And I'm sorry. And if we consider, uh, I'm sorry. Um, yeah, and we consider just the first layer. And we have the hidden layers in front, and will be like incredible amount of parameters and everything. So in convolutional layer, because we're sliding the one kernel, we limit the amount of input element that can affect one output element. So it's shown clearly on this image. So we have x1, x5 as the input and s1, s5 as the output. But now, not like here when everything is connected to everywhere. Let's say x3, if we do convolution by the size of 3 and we like slide the 3, like x3 affects on the s2, s3, s4. Yeah, and it's allowed us to store less parameters, and it just significant improvement on efficiency and decrease in memory requirements. So the second motivation behind the convolutions using convolutional neural networks is parameter sharing. So continuing the comparison between MLP and convolutional neural networks, before each output element had its own like set of parameters that affect it, and moreover, different output elements had different set of parameters. So they didn't share the parameters that affect it. So each output had its own parameters, and they were different, and it was like a lot of parameters. Now, because we're sliding a kernel affects like everything. So we share the parameters in the kernel. The output shares the parameters in the kernel. Over here in the image, you can see the example of it. So let's say the one color means like one parameter. So and over here you can see each of those have is being affected by each of the parameters we have. It's not that much in efficiency improvement, but it's more for memory requirement because we don't need to have like a lot of parameters. And the third one is equivalent to translation. So yeah, to denote it formally, we can denote f of x to be equivalent to g of x if uh, f of g of x equals g of f of x. So if we apply, so in case of the convolution, we care about if convolution is equivalent to the translation in the function g. So it's a function that changes the input of the function f of x. So let's say g of x equals like f x minus 1 or something like this. Yeah, so when we're using convolutional, like whenever we move something in image, the kernel will still like go over it, and the representation will also move accordingly. In this case, let's say if we need to detect something in an image, we can do it whether it's located at right upper edge or low left edge. So let me continue on a theme of the forward propagation for the convolutional networks. As it's explained in this note, like how it was explained how we do the convolutions, like we slide and everything. So let's think how we can like implement it first, like mathematically, and then how we can like efficiently code it. So suppose we have, for simplicity, for the future, for the in our presentation, for the future, for the forward propagation, backward propagation, I'll consider like input images, input square images with straight one and no padding. Uh, uh, so let's say we have let's say let's say we have input I with the shape h times c, where h and h is the square dimensions, and c is the amount of channels. And the kernel is also k times c, which is square kernel. So let's denote the convolution. This formula just represents what was explained in this node, but more mathematically. So it will come in handy when we will think about backpropagation, when we will try to derive a formula for backpropagation. Yeah, so it's an output matrix for the current kernel size. Yeah, because we use. Wait, what happened? Yeah, because we use the straight one and panic 0, the size of that matrix will be h minus k plus 1. So yeah, in terms of coding for the formula of convolution, there are several ways to implement it. As I was searching on the web, one of them might be just straight brute force with bunch of nested loops for channels for the size of the matrix. But there is also other ways we can like make it more efficient. One of them is somehow turning everything into a big matrix multiplication, and then there's even faster way using Fourier transforms. So while brute force solution is straightforward, the other two ways are not that easy to visualize and understand. So let's consider them. So let's check the matrix. So how we can like turn the convolution into big matrix multiplication. So it's faster than just brute forcing into the loops. So the intuition behind this approach is to build like a new matrix, and the new matrix. So as you can see here, so we have our receptive field of our kernel. And the new matrix will have each row of the new matrix will have the flattened receptive field. Each receptive field flattened. So you can see here, this one is this one receptive field. Over here, this receptive field is this one. So yeah, So now if we just flatten the kernel, and we'll multiply this much the flattened kernel by this matrix, at the end we'll get the output matrix also flattened. So at the end we just need to reshape it back to its size. So yeah, I'm gonna go over the code uh, from the blog post I saw earlier on this topic. So yeah, if you want to check out, it's here. It's explained, I guess, better. Yeah. So so let's say now our X is in shape of like the batches, channels, and one and two are the sides of the input image, input to our layer, and the shape of the kernel is K1, K2, and also C. There was this mistake here. Yeah, the CH should be the same for them. And first we're gonna start, so by start IDX, we're gonna say the array of all the possible um, starting indexes for receptive fields. So what I mean by starting index is if you have a receptive field, so the element that has the index 0, 0 in relation to that receptive field. So let's say in this receptive field it's 10, in this receptive it's 1, 2, and so for this matrix, the starting index, it will be list of all of all of those. So so from 1 to 5, from 5, so this square, yeah. So this area would be the just list of
Oh,
elements in this area would be the starting index. Wait, what?
oh, okay. I just want to
Did
make
you have any
sure.
comment?
Seems there is some delay of the network, but now it is fixed.
Ah, there was
Okay.
delay of the network.
But
What did you? What
your
was on?
screen, yeah, your screen. But now I can see the matrix because previously I stuck in the previous node, but now I can see it. So you can
I'm
keep going.
sorry. Is there any, like delays and my voice is unclear or anything like that?
Yeah.
Oh, yeah,
Um,
yeah. You could
but
just
seems
tell
now
me if it's
now
happens.
it is I can see the node you'd like to present since it's stuck to the previous node on my screen. I
Mm,
don't know whether everyone else can keep with the pace.
uh, yeah.
Okay, so
Sorry.
maybe
Did
now you can.
everybody? Should
Uh,
I start over of this note? Start again on that note?
no, you can go on. You can just keep with the go on about this matrix.
Ah, yeah. So the starting index variable will be the starting indices. So the 1, 2, 3, 4, 5. I'm so now I'm just talking how to implement this, like how to implement this big matrix in a code. So over here, the starting index will be. So this is actually how we get that. So this is the whole code how we get starting index because like our kernel in this case is the 3 by 3, and so just need cut out the index of 2 here and index of 2 here, and we get the square. And the square will be our the flattened or the flattened matrix of this matrix square matrix of this will be our starting indices. This as I explained, yeah. So like 1 will be starting index for this receptive field, 2 will be starting index for this receptive field, and 10 will be starting index for this receptive field. So and also. The variable grid over here is implemented. So as you can see over here, this is also flattened. Uh, so we have the 3 by 3 kernel, right? And in this case, and we grid is just a list of all the indices in relation to receptive field. So it's basically wait. Yeah, so it's basically, so if we add the starting index to the whole NumPy array, in this case, we'll get the receptive field, the indices of the receptive field itself. So yeah, those indices are kind of showing the indices of uh, I'm sorry. Yeah, so the I'm sorry for that. So the grid uh, so the so the grid is showing the relationship between different indices of the or in the receptive field. So yeah, so if we add the starting index to this array, any starting index, we get the indices of the whole receptive field. So this one, if we add this, we get the matrix of indices. This matrix will be the shape of matrix what we need, the big matrix which row. But then, but instead of the numbers, it will be indices, and we just need to paste the actual values of these indices in the place, and it's done here uh, with this function take in an NumPy, and you pass it in the you pass you pass it there in an array, and then kind of some list of indices, and at the output you get like the big array where the indices switch to the values of those. I'm sorry, I kind of got kind of weird here, but yeah. So this is how this is how you write like implement the convolutional neural network in terms of a matrix multiplication. So the code is here, and you also can check out the resources. And finally, the faster implementation of convolution is fast Fourier transforms. So the convolution theorem states that convolution of two signals is a pointwise multiplication of their Fourier transforms. So if we take like an inverse of products of two Fourier transforms, we can get the convolution of two signals. So here, this is how it can be done in the Python. Just two lines. But we will need the target dimensions, the output dimensions. Yeah. The code from here was taken from resources, from the video, from one of the YouTube videos. You can check the whole video here. And this like implementation of that was introduced in this paper. So now now we know about the forward propagation. Let's go to backward propagation. And backward propagation basically works the same way as works as multi-layer perceptron. We basically do a forward propagation, get the cost function, and we need just to get all the gradients of all the inputs and all the parameters. So this is so we already implemented the forward propagation formula, and convolutional operation is heavily involved in back propagation. The formulas for the gradients of the input are the following. So let's say over here, so this is gradient for the parameter filter, and this is gradient for the input at each point of the at each point or at each convolutional layer. So as we can see over here, this convolution of it's back propagation also based on convolution. Over here it says full convolution. It means that we have to add the according padding, so the output has the same for convolution. We have to add the padding, so the output of the convolution will be have the same shape as the input. And yeah, over here it's like an idea node. I was trying to derive the form of backpropagation myself. So here, yeah, I'm actually not sure. I just an idea node, so I'm not. It's supposed to be checked, I guess. So suppose we have an input I, HHC, shape of HHC, kernel, KKC, and the output, which is supposed to be K minus H minus K plus 1.
Sorry for interruption.
Yeah.
Okay. Oh, it seems that each time I speak up, then the network becomes yes. Because previously yeah, I don't know whether it's the problem with my network or it's with yours. So now I can see your derivation, but previously I can't. Yeah.
Wait, is everybody experiencing the same problem?
Yes. Can anyone tell me whether you can see Reinbach's derivation of back propagation?
Can you see that?
Yeah, I can see it.
Okay, great.
I was able to see it, right.
Mm-hmm.
And I feel like you're doing a great job. I'm really enjoying your presentation.
I'm sorry, I'm kind of, yeah, I became kind of weird because I'm not feeling that well today, and I'm sorry about I'm sorry about what, like the stopping over here in this note.
The
Yeah,
only
so
thing is I have difficulty reading this specific node. Can you click that image?
click, okay, well, like, is it better now?
Click that image. Have you clicked
Yeah,
it?
I clicked that. I clicked on the
Yeah,
on
I
the
think
image.
yes, there is some delay of the network. Yeah.
Yeah. There is a delay. I agree. So for images, please click and just scroll through it. Can you scroll, go up and down?
Yeah, I can scroll, go up and down. Yeah.
Great. Go ahead, please.
So yeah, for simplicity, also let's forget about the bias and just like just for simplicity. And for simplicity, also take the squares, the square input, the squares kernel, and so now so input is the shape HHC, kernel is the shape KKC. Output, because we have using no padding and no trace, is H minus K plus 1, H minus K plus 1. So now consider the previous formula. Okay. So remember the formula I put on the previously, so now we can use it. So the formula is having, so this M, so this index M and G, Mn indexes for the sides of the matrix, and G is for channels, and it's just multiplication of those. And we can let's try to switch variables. So ij is the indices in the output, and then it's mn is the indices like on the kernel and image. So let's take another variable a just denote a equals I plus m and b equals j plus n. So just reminder, I and j go over the sides of the output, the h minus k plus 1, and mn goes over go over the kernel sides over here. So so now, because we have m goes from 0 to k minus 1, we can conclude those inequalities. So a also can go from I to I plus k minus 1, and the same for j. B goes from j to j plus k minus 1. And we just switch, so take the mn and put, like, just switch into a and b. It will be here. So a goes from I to k minus 1, and b to j k minus 1, and everything like that. And also, so we can conclude. So we can conclude is if if I, A, and B are in those boundaries, then we actually can take a specific um, oh, that was bad image. So yeah, but we can take a gradient from Sij to Iabj. If AB, so we have, so let's say now we fixed I and J, and if A and B in those boundaries, the gradient of that related to that will be just K with those indices. Over here is just G. And because we have this inequality, we can kind of swap it. So we can kind of we can kind of swap it. So now we fix A and B, and if I and J in those inequalities, we can say that the gradient is this one. The K at this at this indices A minus I, B minus J. So so denote Dij the matrix of the gradient in terms of the output. Uh, and as you see in future why we need, let's add a padding to the Dij. So we add k minus 1 on each side. So from now it's before it was h minus 1 k, and we add k minus 1 on each of the sides, so we add 2 of k minus 1. So now a new shape is h plus k minus 1 and h plus k minus 1. And now if we denoted d thing, and we can show that how it's connected. So diy is so-called d prime I plus k minus 1, dj plus k minus 1. So because we just added the k minus 1 paddings to each side, we can have this one. So let's go to the next page. So now, so now we can take the this usual our favorite chain rule that works for the backpropagation for the input. The J, A, B. So now we just take an arbitrary ABE index for the input, and we sum of all of the SI that that is affected by that can be affected to sum over all IJs, uh, so that IJ is affected by IABJ. ABG, yeah. So we proved earlier that if those inequalities hold, we have this equation. And if those inequalities don't hold, basically it means so ABJ just doesn't affect this one. So we can conclude that the gradient of this particular index of I is equals to this sum. So the I goes from A minus k plus 1 to A, and J goes from B minus k plus 1 to B. And we have this equation. So now, because because I already had the formula before, so now we can try switching a variable. So now let's take also a new matrix of k prime, I guess, or how it's called. So that it's a reversed 180 degrees. So it's like flipped x-axis and flipped y-axis. So any k ijg would equal to k minus 1 of k minus 1 minus I and k minus 1 minus g. So now we can just transform this into just ki. We can just transform this into this one and this into this one. But before we need to also apply a new variable. Let's say c equals I minus a plus k plus 1 because now we can say from the c goes from 0 to something, and this is the same j minus b plus k minus 1 because now we also can go d from 0 to something. So if we do this, that means C and D, because I goes from a minus k plus 1 to a, so C goes from 0 to k minus 1, and D goes from 0 to k minus 1. So C goes from 0 to k minus 1, D from 0 to k minus 1, and we can flip the k over here. So so we have a D of C plus A and D of C plus A and D plus B. And as you would remember, this is a form of a convolution. So it's like so now we can conclude that for the current channel, the gradient of image is just convolution of rotated kernel plus a parent D. And because before we were talking about full convolution, and it's the same thing that if we pad D, just normal convolution or the full convolution with a parent D. So this is how I derived yeah, this is how I derived the formula for backpropagation. I was using those sources. So there's two very good articles on how to build an intuition. You'll see those in the resources. Yeah, so those resources articles show like on those small examples how the backpropagation is derived and everything. Also, maybe share also, just to note a very good visualization tool for the convolution. We can over here we can like yeah, it's not invented by me, but just very good resource for visualization of the convolution. Yeah, I'm sorry for my weird presentation. Yeah, today, but I guess that's it.
In general, in the next presentations, so whenever you feel like there is a network issue or for any reason you cannot just see the screens synchronously, you can just walk through the nodes as the presenter is explaining them. And I feel like it will be very helpful if the presenter just sends the title of the nodes before their presentations, like the list of nodes they want to present in the channel or in the Google Meet chat session, so that we can just look for those titles as you go through them, as you present them.
Yes, or maybe I can help to share the screen. I can share my screen and show you the notes, so the presenter can keep speaking. Yeah.
Yeah, that would be also very helpful.
Yeah, I'm sorry for network connections and yeah for coughing. I'm not really thinking.
You did great. I appreciate it.
Is there any feedback on the content or anything else?
I feel like today in general we had. Is there any other presentation, first of all?
No.
So I feel like today we had one of our best meetings so far. We had really good presentations and the topics are very interesting. However, the two research questions we have right now in our channel, these two research questions are not about convolutional deep nets. Most of the focus today was on convolutional deep nets, and so if you are interested to continue with convolutional deep nets, maybe we can work on research ideas about specifically convolutional deep nets. If you are, so I also see people who are not presenting in our meetings. If you have other interests, like if you're interested in applications of deep learning, right now, the two research questions we have are very theoretical. If you're interested in applications, we also have research questions about applications of deep learning. Specifically, there is a research question that Professor Rezek and I discussed for a while, and it is just on the table. I'm not able to work on it right now because I'm just exhausted with a lot of other projects I'm working on. And so if you're interested, that can be a great research project. We have a huge data set to work on, and that is just about application. Just share your interest with us so that we can tailor the research questions based on your interest, but try to get engaged in the discussions and presentations. Otherwise, when we get to the point that we want to work on research papers, you may not be able to get involved in the research because you have not been active throughout the semester.
I apologize for interrupting you. I'm just interested, what are these questions? You told me about Voronoi-based model, and what is the second one?
You can check that in our detailed research plan under the file of our private channel.
Okay, sorry.
Never mind. Okay, so is there any more comments or questions for today's meeting? Okay.
I just want to add a little bit about the other project that I was talking about. So right now we have 2 research questions. They are theoretical questions. It's not about applications. Like, none of these are about applications. So check these out on the document that you has shared with you on the channel. Those are possibilities of research papers to work on. The other project that I've not shared on the document yet, but I can definitely help you with working on that, and I'm also interested in that, is about just application and a specific application of LSTM. So we have not worked on recurrent neural networks yet. So in future presentations, we may have presenters talking about recurrent neural networks. And I'm not sure if you have gone too far to the deep learning textbook or the Coursera specialization to learn about LSTM and its applications. But so this specific project is about LSTM. And the idea is, the research question is, there are many research studies on how to improve memorization and learning, like long-term learning, using deep learning models. And when I'm talking about long-term learning, I'm talking about human long-term learning, like students. And many different algorithms have been implemented and tested. So if you're interested to learn a little bit about the background, Duolingo has a lot of papers, like they publish almost every year in different conferences about their algorithms. And those algorithms are specifically tailored towards the language learning on Duolingo. There are also other algorithms out there for, like, there is a category of, they call it spaced repetition algorithms. And so this has a very long history. Like, previously they were just deterministic algorithms. There was no AI involved in those algorithms. Now, in more recent papers, we see a lot of deep learning applications, specifically like some of them are recurrent algorithms, because it is necessary to use recurrent configurations to basically memorize the timing of answering previous questions to learn from for a specific student on a specific topics. And so in our research project, so previously we published a very simple model for spaced repetition, and an experiment we conducted in one of the School of Information classes on 200 students. Now I'm working on a larger paper that we conducted the experiment on over 1,200. Yeah, over 1,200 students in 8 semesters. And so this is kind of a major paper that we're currently trying to submit it to Science magazine, and we'll see what happens. But This is just about UX research of the project. It's not about deep learning at all. Professor Resnick and I have discussed how to use LSTM specifically for a more efficient algorithm for improving the questions to ask students, specifically based on their log data of their answers to previous questions of the topics of a specific course. And we have a large data set. Right now, we have over like hundreds of thousands of rows in our data set. However, there are recently, last week, I was informed that there are more than 1,700 teachers, I mean, instructors, including university professors and high school instructors in the US who are using my practice tool, I mean, my space repetition system. And we have the log data for all of them. So I have no idea what, in terms of the dimensions of that data set, but I believe that would be a perfect data set for an LSTM model. And I feel like if we can find a more efficient algorithm, that would be also a major paper for improving the efficiency of students' memorization and learning over time using a personalized practice tool, like how to design this algorithm for a personalized practice tool. If you're interested in that, just let me know so that I can also share a paragraph about that research question in the document that you has shared.
Oh, also, can I ask? I'm sorry for interrupting. Oh, did you finish? Because yeah, I made a mistake in my presentation about the full convolution. Full convolution is not the convolution that preserves the shape. It's a different convolution.
Right. And we had some nodes about convolutions and also the other topics, but they were not necessarily related to the two research questions that we currently have on the document, right?
Yeah. So it's mostly LSTMs and like recurrent neural networks.
Right.
I see.
So
let
me clarify this. Those research questions are not about recurrent neural networks. They're not about LSTM. The new research question that I was just talking about is about LSTM. And I'm saying if there is interest in working on like an application of LSTM, I can also share that on the document. Otherwise, we can just continue with the two theoretical research questions that we have in the document.
I see. I would be interested.
So just let me know your interest, and we have many research questions available that we can share with you, and we can focus on whatever the community likes. So there is no lack of research question in this community. We have good research questions. We have data for each of the research questions, but we want to work on what the community likes. If you like the two research questions that I've put in the document right now, we can continue with those research questions. If multiple students like one of the research questions, other students prefer like the other research questions, we can like have two or multiple groups of students, and I can support you to work on multiple research questions. If you have your own research question, you're interested in another research question that we don't have in the document, feel free to also share those research questions. No one has added anything right now, but it's just me adding two research questions. And I can add this new research question as well if you're interested. Just let me know what you like to do.
Yeah. Do you think it's helpful if so everyone can check our document, and if you are interested in one of the research questions, or 2 of them, or even 3 of them, you can leave your name under that question, so we can have an idea of everyone's preference. Okay, so is there any questions? So Jiayun, are you here?
Yes.
Yes. Can you stay up with me for a little more minutes? I have some question about the notes that you proposed previously. So I think anyone else, if you don't have questions, you can feel free to leave now.
Thank you. Bye-bye.
Okay, I will stop recording.